So if you've been following along in some of the lectures, you'll notice that we don't really share much of the mathematics up until now. There are a lot of proprietary IP moats that we don't really like to expose in this venue, but in this case, for this master law, we have actually written a pretty dense book here. We've got there's 12 chapters, 13 chapters, including chapter 0, and we've written a very dense book. So like you can see that when we discuss the master law, we have a nice introduction, and then we have a very rigorous mathematical treatment of it, and then finally we get into the example code here. And you'll see that if we go back to here, the truncated version, we're dealing with random SVD, we're dealing with fast Fourier transforms and discrete wavelet transforms, we're dealing with principal component analysis and sensor placement. So these are not in themselves proprietary. These are common tools. What we're doing though, the master law, is a bit proprietary here, but we're going to share it anyway because it is a precursor to being able to assemble the massive systems, cyber intelligent systems that we're talking about when it comes to agentic negentropic dynamics. And there are some extensions to this, like for example, W here is a fixed value, but in our extensions it can be a variable value. And there are also, rather than just using Riemannian manifolds, we can use many different types of manifolds. So these are some extensions that I'm not going to share in this conversation, but I do want to go through this so that we can see the power of using this master law and why it's so important. The other thing I'll say about this is even though I'm going to be sharing some of the mathematics here, this will be available for training for our partners because it's just a key and important concept, this master law. And we'll make this available. We'll help to train our partners on this. But in this conversation, I'm going to keep the terms light. I'm not going to get heavy into the math. I'll show it here for you, and if you're into math, you can follow along. But otherwise, I'm just going to talk this through. In a way of introduction, imagine you're just standing in a giant library. Imagine that every bookshelf holds a different subject. One shelf, it might be for image processing, but another might be for robot control, another for weather prediction, another for machine learning. You might have another shelf for signal detection. And there's more, right? So each of these shelves, it's going to have its own language. It's going to have its own tools, its own community of experts, but these experts rarely talk to one another. For example, a robotics engineer and a Netflix recommendation algorithm designer, they might share a coffee. Sometimes they might talk about mundane things, but they'll have almost nothing to say to each other professionally, even though underneath the surface, they're actually working with the same fundamental problem. So what is this problem? Well, the problem is that the world generates really enormous, messy, noisy streams of data. And we want to understand this data, what's actually happening underneath all of that noise. We want to be able to predict what's going to happen next. Sometimes we'd like to be able to impact or intervene in that system or steer things in some way, maintain stability of the system, or steer the system towards some better outcomes. Now, every field that we've listed above and many, many more, we're trying to do exactly that. Each system, they have each independently developed really brilliant tools, but because those tools were invented in isolation, they often speak different dialects of the same language. I do have to take a step back here and talk about the type of systems that we're dealing with, systems of interest in the modern world. We're not dealing with simply deterministic systems anymore. We're dealing with systems that have high degrees of freedom. They're highly complex. They have many, many, many different high dimensionality to them, and these tools of the past, which have been designed for the deterministic world, they need some updates to be able to work with high dimensional problems that we have to face today. And so what we're describing in this conversation is a single unified framework. We're calling it the master law. And this framework speaks all of those dialects at the same time. However, it's not just a simplification. It's not a simplification that ignores all of the details. It's a genuine mathematical backbone that connects randomized matrix algebra, image compression, outlier detection, regression, decision trees, even neural networks, dynamical systems identification, robust control, reduced order modeling, online optimization. It connects all of these into one interchangeable system. And every technique that we cover in every chapter is a specialization, it's a projection, or it's a particular lens of this one underlying structure. So we're going to walk you through all 13 chapters here, and we're going to just speak in plain languages, no equations. Every concept will be named and explained in a thoughtful, curious manner, but we're not going to expect anyone to be a specialist. So let's just step into the first conversation about this master law. Let's just start with something concrete. Imagine you're watching a complicated physical system evolve over time. It doesn't really matter what that complex system is, remember, this is a unified master law. So it might be a drone that's navigating in turbulent air. Maybe it's a financial market that's responding to the news, or a human heart that's beating. It might be a chemical plant converting raw materials into products. In any case, at every moment, the system that you've chosen, the system that we're observing, it has a state. That's a complete description of everything relevant about that system right now. Now, the state might be the position and velocity of every moving part. It might be the concentration of every chemical. Maybe it's the price of every asset. But in general, the state is a very long list of numbers. Now, the world does not let us observe the states perfectly. We have sensors, but sensors are imperfect. Those sensors, they give us just a measurement. They give us a noisy partial, like a filtered window into the true state. And the system itself also is not sitting still while we're watching it. I mean, it's being driven by input. These are the controls that you apply. They're the disturbances the environment applies, and they're also just a random noise that's always part of nature. And the system is responding to all of these, and the state can change accordingly. Okay? So the fundamental challenge is this. Given a stream of noisy measurements coming out of a system that's being pushed around by inputs and noise, can we figure out what the state really is? Can we predict where it's going? And if we have some kind of a knob that we can turn, are we able to turn it in a way that, well, can we turn it wisely? Let's put it that way. Now, the master law begins just by naming the players in this drama really carefully. The state, called Xi, that's a Greek letter, the state lives in a high-dimensional space. Think of it as a point that's floating in a room that might have thousands of dimensions rather than just 3 dimensions. Okay, so the state can be very high-dimensional. Then there's the input. We're calling that U. This is what you push into the system. It might be a control signal or some external force of some kind. And then there's the output, which we call Y. That's what we can measure. That's the sensor reading that you actually get to see. Then the geometry of the space, where the state lives, is not an accidental geometry. This is a structure that we call W. Now think of W as a set of weights that tells you which directions in the state space matter more than others. Some directions are energetically important, but some are almost irrelevant, and W encodes the importance. And everything that follows after you get that W value respects W. Everything you do later respects W. So the master law says that the state is going to change over time according to a precise recipe. And the recipe has 3 different ingredients. The first ingredient is structure, because every physical system will have some underlying geometry. There's going to be conservation laws, symmetries, the way that energy flows from one part of the system to another part. Now, some of the structure is conservative. That's energy that sloshes back and forth without being lost. Think a frictionless pendulum, for example. Now, some of the structure is dissipative. That's going to be energy that leaks away, like a pendulum with friction, maybe. And the master law separates these 2 contributions using 2 mathematical objects. One called omega captures the conservative lossless oscillatory part. The other called lambda captures the dissipative energy losing part. And together they describe how the system would evolve if left alone, with no input and with no noise. Remember, the first ingredient is structure, right? The second ingredient is going to be energy. Now the framework uses a function called the Hamiltonian. We denote that with an H, obviously, and it's pronounced roughly like its name, Hamiltonian, which is essentially, it's a bookkeeping device for the total energy stored in the system at any moment. The state changes in a direction that is related to how the energy landscape slopes. So think of a ball rolling down a hill. It moves in the direction that reduces the potential energy fastest. And the Hamiltonian plays the role of that hill. And the gradient of the Hamiltonian, the direction of the steepest descent, that tells you which way the system is being pushed by its stored energy. Geometry here. Energy on a geometric landscape. Now the third ingredient, we already have structure, we already have energy, we have to include noise, because real systems are always being buffeted by some types of random disturbances. And the master law includes a noise term, driven by something called a Wiener process, or Wiener process, depending on how you pronounce Norbert's name. The mathematical model of a pure continuous randomness. Think like Brownian motion. The noise has its own structure. The noise is captured by a matrix called sigma, and sigma describes how large the random kicks are and in which direction they tend to push the system. Now if you put these three ingredients together, you're going to have the master equation. The state at any instant is changing at a rate determined by the structure of the system's geometry, the gradient of its stored energy, and the effect of the input, and also the random noise pushing it around. This is written as a stochastic differential equation. This is just an equation that describes continuous change in the presence of randomness. Computers do not work in continuous time. Computers take snapshots at regular intervals, like tick, tick, tick. They're just taking one picture after another. So the master law is also going to provide a discrete twin, an exact counterpart of the continuous equation that describes how the state at one time step maps to the state at the next time step. Now this is not an approximation. It's the same physics expressed in language of sequential snapshots rather than a continuous flow. The discrete twin uses a flow map. This is a function that takes the current state and input and computes the next state. And then it adds a noise term that kicks the state randomly at each step, with the kicks drawn from a distribution that matches the continuous noise. Then we have to think about Ito balance, which is just simply tracking energy under uncertainty, because this is going to be a third formulation. The Ito balance is less about the state itself, and it's more about the Hamiltonian, the energy as it evolves. The equation tracks how the total stored energy changes over time, accounting for all three sources of the change. The drift due to the conservative and dissipative structure, also the diffusion due to the noise, and something subtle that's unique to stochastic calculus. Here it is. When you have a function of a randomly moving quantity, the function's average rate of change picks up an extra term called the Ito correction that comes from the curvature of the function interacting with the noise. And the Ito balance makes this explicit, which is essential. It's essential for rigorous analysis and for making sure that the reduced order models, that they don't accidentally violate the energy budgets. So we have to include the Ito balance. And finally, we're talking about ports, how the system talks to the world. The master law has a set of ports. These are named connection points through which the system interacts with the outside world. There is a port for the conservative oscillation, there's a port for the dissipation, there's a port for inputs, there's a port for outputs, and there's also ports for lift. Lifts, they make nonlinear behavior look linear. We'll talk more about lift in a minute, but the ports are not just for bookkeeping. They're actually the sockets into which every technique in every subsequent chapter is going to plug into. So that when you do compressed sensing, for example, you're using the output port. When you design a controller, you're using the input port. And when you build a neural network encoder, you're constructing the lift. And the ports are what make the whole system modular and interchangeable, such that we can begin to build massive modular systems. Let's talk a little bit more about the lift, because this is one of the most powerful ideas in the framework. It's denoted with psi, the Greek letter psi. Most interesting physical systems are nonlinear. which means the equations governing them involve products and powers of the state variables, not just the sums. Okay, but many of our best mathematical tools only work for linear systems. The lift is really an important concept. It's a mapping that takes the state in its original nonlinear world and it re-expresses it in a higher dimensional space where the dynamics look linear, so that we can apply linear tools to nonlinear systems. So think of this as maybe you have a crumpled up piece of paper, okay, and it's in 3 dimensions. The paper is complicated, it's all crumpled up. But if you can find the right way to lay it flat in a higher dimension space, it becomes simple, it becomes straight. And the lift does that for dynamics. And this idea connects directly to the Koopman operator in mathematics. And this is what makes techniques like extended dynamic mode decomposition work, the EDMD. We'll talk about EDMD and other methods of dealing with dynamical systems, but the concept of lift is key to all of these methods. All right, so in closing this chapter 0, every technique in all of the chapters that follow, it's just a way of discovering and approximating or using the master law for a particular system of data. The randomized SVD discovers the geometry W. The Hamiltonian regression discovers the energy function H. The neural network, it learns to lift psi. The reduced order model compresses the state to its most important directions, and the robust controller uses the master law structure to guarantee stability despite uncertainty. Then there's a parametric library, which stores instances of the master law at different operating conditions, and it interpolates between them. But in every case, the question is the same. How do we identify and compress and use this underlying physical structure from data in a way that respects the geometry, quantifies the uncertainty, and remains safe and stable all at the same time? Okay, we've had a nice discussion of the master law in general. We want to move now to just the randomized SVD. And I can go back to the book section here, and you can go ahead and pause anytime you want and read through some of this. I have no problem with that. I'll scroll down a little bit here, and you can pause at any point. You scroll down to here, scroll down to here, you can pause it and look through all this. And then when we get into the code, I'm not going to burden you with a bunch of code here, but I will go down now to our chapter 1, following the code sample here. And we're going to talk about this randomized SVD, our SVD in the master law. So SVD deals with the curse of dimensionality, really. Modern data sets are just enormous. You know, a fluid simulation, it might be tracking the velocity at millions of grid points, or a neuroimaging scan, it might record activity at maybe hundreds of thousands of voxels. A climate model is going to be carrying probably billions of state variables. And working with these types of data sets in their full size is just computationally prohibitive. I mean, and often it's unnecessary because most of the interesting variation in that data is going to exist in some much lower dimensional subspace. But we need to find that subspace. That's the challenge, to efficiently find the high energy subspace in the system and discard the low energy signals. A classical tool to do this, I should say the classical tool, is singular value decomposition. This is the SVD, the classical SVD. And it's the most fundamental operation in all of linear algebra for this purpose. And the SVD, it basically takes any rectangular table of numbers, any matrix, and it finds the skeleton, the most important directions of variation, and it ranks them in order of importance by their singular values. And if you keep only the top few directions, and if you throw away all the rest, you're going to get the best possible low-rank approximation of the original data in a precise mathematical sense, such that it's small enough to compute upon reliably. But SVD is old. Our SVD is newer. And what's the difference? Well, the problem is that computing the exact classical SVD, if it's a truly huge matrix, it's going to be too expensive. Like for a matrix with millions of rows or millions of columns, the classical algorithm is so slow that it just becomes impractical. It can take weeks to resolve. And so enter the randomized SVD, the RSVD. This is a remarkable algorithm that computes an excellent approximation to the SVD, but it does so at a fraction of the cost. And the key insight, it's so simple it's almost shocking. Instead of working with the full data matrix, you multiply it by a small random matrix. It's just a sketch. And then you work with the result. And the random matrix acts like a sampling probe. It queries the column space of the data matrix. It captures the directions of the largest variations with high probability. And then that sketch is much smaller than the original matrix. So subsequent operations on it are cheap. So you're only using the expensive SVD on a proxy, a small condensed proxy. And then we're going to be using optional power iterations. These are repeatedly multiplying the data by the data matrix, and then it's transposed so that you can sharpen the approximation. But anyway, the result converges quickly to the true dominant subspace. And this was a huge innovation that came out of Yale, the RSVD. Now, here's where the master law geometry is entering in. In the plane SVD, all the directions in the state space are treated as equally important. But in physical subsystems, they're not equally important. Some state variations carry a lot of energy, and others carry very little. Some sensor measurements are highly reliable, but others are noisy. The weight matrix W encodes this importance, and the RSVD algorithm is modified to respect W. So instead of working with the raw data matrix, the algorithm first applies the square root of W to weight the data before taking the SVD. This ensures that the low-rank approximation is optimal in the energy-weighted sense. It keeps the directions that matter most physically, not just the directions that have large numerical magnitude. And so what comes out then is, or the output of the SVD, of RSVD, is a set of basis vectors, the columns of two matrices called V sub r and W sub r. These form a biorthogonal pair. The right basis vectors, V sub r, span the most important directions in the state space, and the left basis vector, W sub r, are the corresponding projectors that extract the reduced coordinates from any full-dimensional state vector. The pair together define a low-dimensional coordinate system for the dynamics, a reduced space of dimension r, where r might be 10 or 50 or 100, compared to the original state space of millions of dimensions. The reduced order operations, the conservative structure omega sub r, the dissipation lambda sub r, and the energy matrix Q sub r, these are all then computed by projecting the full-dimensional operators onto this basis. The result is a miniature version of the master law living in the reduced space that captures the most energetically important behavior of the full system at a tiny fraction of the computation cost. And there comes a guarantee. Well, there's a guarantee and a cost. I mean, the SVD comes with the mathematical guarantee that the error it makes in approximating the dominant subspace is, with high probability, only slightly larger than the best possible error achievement by any rank R approximation. The best possible error is the r plus 1th singular value of the weighted data matrix, a quantity that drops rapidly for most physical systems, meaning that a small number of the basis vectors captures almost all of the interesting variation. The computational cost is dominated by forming the sketch, which scales with the number of state variables, the number of snapshots, and the desired rank, and is drastically cheaper than the exact SVD for large systems. Once the basis is in hand, then the master law is projected onto the basis. The result is a reduced master stochastic differential equation, the same mathematical form as the original, but now the state vector has only r components instead of millions, and this reduced equation inherits the structure of the original. It has the same conservative and dissipative parts, the same input ports, the same noise structure. So it's not just a numerical approximation. It is the master law itself, compressed into its most important modes. Now, every downstream technique, every control design, uncertainty quantification, sensor placement, all of it can then operate on this reduced system at a cost that is proportional to R, not proportional to the original enormous dimension. So what we have here now is the regular SVD with an upgrade, because it has energy and uncertainty dynamics baked in through the master law. This is critically important as a first step. So here we can scroll down. You can read the intro here, and then for the mathematics, you've got your canonical master statement, your one paragraph scope, your states, ports, and parameters. You can read through this if you'd like. I'll just scroll down and you can pause wherever you'd like. And when we get to the code itself, we can stop, because this code is workable code. You can copy paste it directly into a Jupyter cell and it'll run. But in any case, we're going to talk about fast Fourier transforms and discrete wavelet transforms. So compressing images and signals. And we're going to use images mostly here because it's easy to get your mind around. The idea here for FFT and DWT is that not all data is organized just as snapshots of a dynamical state. Images, audio recordings, medical scans, radar returns, these are signals that live in space or time, and their structure is going to be fundamentally different from just that list of state variables that we were talking about up until now. Because an image is a grid of pixel values, and the interesting content, the edges, the textures, the objects, it's organized spatially in a way that raw pixel values don't make obvious. Compression and denoising of these types of signals requires a different set of tools. It requires transforms that re-express the signal in a basis where its important features are concentrated into a small number of large coefficients, while the noise is then spread out across many small coefficients. And two transforms dominate this domain. There's the fast Fourier transform and the discrete wavelet transform. So let's think first of all about the Fourier transform. Everything is waves in the Fourier transform. The FFT is one of the most celebrated algorithms in all of computing. The fundamental idea is that any signal, any sequence of numbers basically, it can be expressed as a sum of pure sinusoidal waves, each at a different frequency with different amplitudes and different phases. That's it. It's not an approximation. It works out to be an exact mathematical identity. And the FFT, it computes this decomposition with, it's very efficient. It's extraordinarily efficient. An algorithm that would naively require operations proportional to the square of the signal length, instead it only requires operations proportional to the signal length times its logarithm. It's a huge efficiency boost. In terms of the master law, the Fourier decomposition is a particular choice of lift. It maps the signal from its original representation, which is pixel values or voltage readings, whatever it is. It lifts it into a frequency space where the structure of the underlying dynamics is usually much clearer. So a system that oscillates at a particular frequency, it's going to have a dominant peak in its Fourier transform, which makes that frequency easy to identify, easy to filter, and easy to control for. So what about wavelets? There is a limitation to the Fourier transform, and that limitation is a global limitation, because a pure sine wave actually extends forever in both directions. So the Fourier coefficients of a signal, they do tell you about its average frequency content, but it doesn't really tell you much about where in the signal different frequencies are going to appear. An edge of an image, a sudden jump in brightness, it has significant frequency content, but that content is localized to the edge location. And the Fourier transform, it smears that across all frequencies. I mean, the sinusoid is infinite length. So that makes the prediction inefficient for signals that have sharp local features. Wavelets solve this problem, right? Because the sinusoidal wave is infinite, but a wavelet is not. A wavelet uses basis functions that are localized in both space and frequency at the same time. A wavelet is a small oscillatory decaying function. It's like a brief burst of oscillation instead of that infinite sine wave. And the discrete wavelet transform, the DWT, it decomposes a signal into coefficients corresponding to wavelets at different scales and locations. And this creates a representation that can efficiently capture both smooth regions and sharp features. The result is that natural images and physical signals can typically be represented with very high fidelity using only a small fraction of the wavelet coefficients. The res can be set to 0. That's with minimal loss of quality too. And this technique is the basis of the JPEG 2000 image compression standard and also many denoising algorithms. So within the master law framework, these transforms are modeled to respect the weight matrix W. Instead of applying the FFT or DWT to the raw signal, the framework first applies the square root of W to weight the signal and then transforms the weighted version. Thresholding is then applied in its weighted space so that the decision about which coefficients to keep is made in terms of the physical importance rather than just the raw magnitude. It's a major upgrade. The master law upgrades both the SVD and the FFT and the DWT. The reconstructed signal is then unweighted to return to the original space. Every time you throw away coefficients, however, whether by Fourier thresholding or wavelet thresholding, you're going to be introducing an approximation error. In a plane image compression algorithm, the error is just accepted as a quality trade-off. But within the master law framework, it's tracked explicitly. The truncation error becomes a contribution to the identification uncertainty, a matrix called sigma ID that accumulates all sources of uncertainty about the system state and the parameters. Now, this matters enormously for control because if you're using a compressed representation of the system state to drive a controller, the uncertainty in that compression must be accounted for in the controller's design, or else the controller is obviously going to be overconfident and it's going to behave unsafely. So we have to have the uncertainty packaged with the master law and carried forward in any future operations. So our framework here provides explicit formulas for how much uncertainty each level of truncation is going to add, and those formulas feed directly into the uncertainty budget used in later chapters for control synthesis, for model validation, for whatever. You're beginning to see the importance of this master law. I'm going to scroll down here so that you can see the mathematics in here. And you can pause and read through this if you like, as a more rich reference, because obviously I'm just covering things at 30,000 feet here. And then we can skip the code and move on to the next chapter, chapter 3, which is going to be PCA, sensor placement, and SOC. This is actually related to a separation problem. Real-world data is almost never clean, right? I mean, a traffic surveillance camera, for example, it's sometimes going to capture a vehicle that parks in front of a sensor. That's going to occlude it for a minute, so you're going to have empty space. A medical monitor is going to pick up maybe sudden electrical artifacts from nearby equipment. A financial time series is going to contain occasional extreme events, crashes, squeezes, manipulations, and these are going to look nothing like the underlying market dynamics. In all of these cases, the data contains two superimposed components. There is a low rank part which represents the regular structured behavior of the underlying system, and that's what we want. And then there's going to be a sparse part which represents these occasional large corruptions and or anomalies. And the key insight is that the anomalies, that you have to be able to separate the anomalies from the stable underlying structure. Separating these two components, we call that robust principal component analysis, or robust PCA. This is one of the most practically important techniques in modern data science, to be able to do that. The classical PCA, it finds the best low-rank approximation to a data matrix by minimizing the sum of the squared errors. And this works beautifully whenever the noise is small, whenever it's spread evenly across all the entries. But when a few entries have catastrophically large errors, now these would be outliers or corruptions or anomalies, then the squared error criterion causes the PCA to distort its entire solution by trying to accommodate for those few bad points. The result is a low-rank approximation that's contaminated by the outliers. So robust PCA is going to avoid this, as opposed to classical PCA. Robust PCA explicitly models the data as the sum of two unknown components. There's a low-rank matrix, L, representing the clean underlying dynamics, and then there's a sparse matrix, S, which represents the corruption, and it separates these. It finds the best separation by minimizing a combination of the nuclear norm of L, which is a measure of its rank, and the L1 norm of S, which is a measure of its sparsity. And then the nuclear norm promotes low-rank solutions, and the L1 norm promotes sparse solutions. So this combination acts as a kind of sort of like a tug of war, a competition that finds the cleanest separation consistent with the data. The optimization problem in robust PCA is solved using a technique called ADMM. That stands for Alternating Direction Method of Multipliers. So the idea here is just to break the problem into two simpler subproblems and then solve them alternately with a coordination step after each round. And the coordination step enforces the constraint that L and S must add up to the observed data. So you're always checking after you take a step. And each subproblem has a clean, fast solution. The L subproblem is solved by a singular value thresholding operation, right? A soft thresholding applied to the singular value of a matrix. And then the S subproblem is solved by a soft thresholding operation applied element-wise. And the two steps alternate until there's a convergence. And you can read through some of this here. But anyway, within the master law framework, the robust PCA is applied to the geometry-weighted data matrix, so that the separation between clean dynamics and corruptions respects the physical importance of the different state dimensions. So the RSVD from Chapter 1 can be used to accelerate the low-rank step, making the algorithm feasible for very large systems. Now, we need to also talk about sensor placement too. Once you have a low-rank model of the dynamics, a natural question arises, well, which sensors should we use? For example, if we have 1,000 possible sensor locations, but we only have 10 sensors available, which 10 placements are going to give you the most information about the system state? This is called the sparse sensor placement problem. Within the master law framework, the answer is found using a weighted version of the classical technique called pivoted QR decomposition. So that's a classical technique, but we're applying a weighted version of it. So the idea here is to apply this decomposition to a matrix formed from the reduced basis vectors, the V sub R from the SVD, weighted by W. Then the pivoted QR algorithm automatically identifies the columns, the sensor locations, that are most linearly independent in the weighted sense, meaning that measurements at those locations carry the most non-redundant information about the state, the pivots. The column indices selected by the algorithm, the pivots are the optimal sensor location. A related problem arises just in classification. This is if you just want to identify which class a system belongs to, whether it's healthy or diseased, whether it's nominal or faulty, whether it's one species or another species, whatever it is. We want to identify the class using as few sensor measurements as possible. And that's where the sparse sensor placement optimization for classification, or SOC. It solves this by finding sparse linear combination of sensor readings that best separates the classes. And it does this by solving an optimization problem that simultaneously minimizes the number of sensors used and the classification error on the training data set. The sensors selected by SOC are those whose measurements are most informative for the specific classification task at hand, which is different from the sensors most informative for the state reconstruction. Alright, so as with the compression in Chapter 2, sparse sensing introduces an approximation error, because you're reconstructing the state from a limited number of measurements, and any state components not captured by those measurements is going to contribute to the uncertainty. So the master law framework inflates the identification uncertainty, or sigma ID, by a term that reflects this truncation, ensuring that the downstream control and the downstream decision-making algorithms, they know how uncertain the state estimate really is. So let's scroll down a little bit so you can take a look at the mathematics for Chapter 3. Here you've got the algorithms and recipes included here. Here are structure enforcement and small convex program. Here is randomized linear algebra. Here is diagnostics and acceptance checklist. All right, so we go all the way down, and then we're going to skip the code samples and get into regression and model selection.